Hello, everyone. My full name is Hydai Tai, but I believe it's too hard to pronounce, so you can call me Hydai. This short one, okay? And I'm the maintainer of the Watson Edge project. It's a CNCF sandbox project, and actually it's just a lightweight runtime. Can run the WebAssembly bytecode and do lots of applications. And I'm also the CNCF ambassador. So in this talk, I will cover at least 4 demos to show how to run your LLM with the Llama Edge software stack, with the Watson Edge software stack. And it can leverage not only the CPU part, but also the GPU part. And all of the hardware-related parts will be handled by our runtime. You don't need to worry about, oh, I have the NVIDIA GPU, I have the Apple Silicon, and I have lots of different kinds of GPU, but it's really hard for user to install the correct version. So we will do this stuff for you. And my slide and all of the information is put in this link. So you can go to this link and you can get 4 demos. And of course, this slide is inside. So let's just start with a quick demo, which is cute, the Watson Edge with the Llama Edge chat model. And let me clear my screen first. So in this example, this is a command, of course, and the most important is that we want to run an Llama 3 AB DN model with our chat application, and of course, you have to specify the promote template. The prompt template, and this is the Llama 3 chat. And I also set the context size to a large one. The default one may be very small. If you ask so many questions, then it will show the error of the context full. So let's start. And when you run this Llama chat, this error, you can skip it, is false positive. And it will show our version you use and the prompt you use, and the content size, and lots of the relation part. And the most important thing is that the only thing you need to do is to specify how many model layers you want to offload into your GPU. The default value we set is 100, which will include most of the LLM now. Let's say the Llama 2 and Llama 3 has only 33 layers. So when we specify a large value, you can offload all of the Llama 3 model into your GPU. And this is the Apple Silicon. So now let's ask a question. For example, what's the capital of Japan? And you will show something, right? And you can say, give me 5 popular books in JSON format. And you will, this speed is because it's run on GPU, so it's very fast. Yeah, so this is the quick demo to show that how you use the software stack to do this job. And you can just, check this code detailed, but as you can see here, we have lots of options, lots of things you can sell by yourself, because you can imagine that this example is trying to create a similar experience with the OpenAI Chat GPT. So there are lots of details you can specify by yourself. Let's go back to our slide. So let's dig into this whole software step. So the first one is why we choose WebAssembly. The whole demos is running in this format. But why we choose it is because that the size is pretty smaller. And especially if we have a normal size to run the previous example, it may be 30 it may be 30 megabytes, but in our example, it only takes 5 or 6 megabytes. So the execution format is pretty small, and so we will have a faster startup time and is nearly native performance. So it's all about the cross-platform issue is that we want to provide this runtime on not only the Linux, the Mac OS, and we will have Windows support later. And of course, all of the architecture we want to support not only the AMD 64, the ARM architecture, then the RISC-V, lots of hardware architecture we want to support. And the most important is that, as you can see, that our previous demo is using the Rust language to write the whole logic, but you can use C or C++ or Golang, Kotlin, and lots of different programming languages to do the same thing, because all of this language will compile into the WebAssembly format, and you will distribute the same format to all of our devices. Yeah, so that's why we choose this format as our execution format. But there is some trade-off. The most cons is that the WebAssembly itself cannot support GPU. But in our previous demo, you can see we use the GPU, right? So we have an extension called the GOSIM neural network, and actually, you can find lots of different GOSIM proposals with the GOSIM prefix. The meaning is that this is the WebAssembly system interface. It will allow you to extend several different API. For example, if you want the file system, if you want the AI inference, if you want the AI training, or lots of different ideas or database, you can define your own APIs with such kind of a proposal. So we define the GOSIM neural network, and there are several basic functions to handle the models. So the first thing is we have lots of different kinds of the load function, because that different models have different options. Let's say some model will ask you to specify the template or specify the temperature at the beginning, and it cannot allow you to modify it later. And some are not. So that's why we have lots of different load functions here. And when the model is loading into the memory, the important thing is that we have to initialize the execution context, which will construct all of the model-relative parameters, such as the context size or the reverse prompt or lots of different metadata will be initialized here. And then we have to handle the I/O part. For example, you need to set the input, you need to get the output. Of course, because that in traditional AI inference, most of the time we will wait the AI model do the whole inference and get the output, right? So it will take lots of times. However, when you are using the LLM, such as the ChatGPT, you can find that it will put token by token directly. It's not blocking, it's streaming, right? So we defined a special part called the get output single, which will only return one token. When I just get a token, I will just return a token to you. You don't need to worry about the whole execution is blocking. And then we have the compute function, which is do the actual inference job. And of course, we have load, we must have the unload. Otherwise, when you load lots of models and your memory will constrain all of the things. Yeah, if you are interested in the details, how we define these APIs, you can go to this link, and you can just get lots of details of these functions. Then let's go back to our runtime, the wasm edge. what we do for the previous demo. Actually, we run the basic WebAssembly, for example, handle the input, output, and do the basic logic things. However, we dispatch or we pass in our AI inference or the LLM inference to the GOSIM neural network plugin. So you can imagine that if you have the different domain want to use this similar software stack, you can have the GOSIM Edge core itself, and if you want to do the LLM job, you just need to give the llama.cpp plugin. If you want to connect with the database, you can have the database plugin. So the idea is here is that all of the extension are plugged in. You can just plug or eject it. That's all. So let's go to the second demo. This demo will show that how we created an OpenAI compatible API server. So you can build your local LLM with your, such as Copilot or core compilation and lots of things. So let's run the demo here. Just clean and okay. So the only thing change is that the previous option here, we also have the the neural web preload. We want to preload the Llama 3 8 billion model, but the WASM file is changed. The previous one is the Llama chat, and now is the Llama API server. And of course, you have to specify the prompt tablet, and also you may want to set the content size, and you want to specify the model name. Anyway, and if you are interested, actually it has lots of options you can do. Just go through this file. Let's maybe tens or hundreds options you can do by yourself. So let's just execute it, and it will give you a simple web UI, so you can ask questions here. For example, you can also just ask what's the capital of Netherlands. Oops. Oops. Let me check. Just try again. Sorry. I have no idea why this is working again. Okay, it's working. So maybe I just recall the demo and show the video, then you will not have any issue. But but the live demo has, it's real. Yeah. So as you can hear, this API server that you can use. Let's just show the code. You can use the Rust, to define all of the idea you want. For example, here there's lots of options you can set. For example, you can set the predict number. You can set the GPU layer. What is the GPU layer is so important, I have to say. If you have a small device or small GPU, there's no way to offload all of the model into your GPU. For example, this model has 4 gigabytes and your VRAM only has 1 gigabyte, then there's no way to offload all of them. But you can offload partial of them. Then it will, still increase the inference speed. Okay, so this is very important if you want to, use all of the software stack with the GPU. You need to take care about this value. And lots of detail, you you can just do it by yourself. And then you can define the main, the execution loop to do the details. For example, this is our main function, and you can just set lots of scenes, and you can also create your own idea, or you can, you can add a new template to a new model. For example, because different model needs different prompt templates, if you are training a brief new model and it's not supported by our API server, you can just edit it and add your own template, and that's all. So the idea is here that we want to bring a framework or a basic idea. This is not the product. This is example for the developers. They can just modify this file and add any idea they want and any logic they want to, to do the thing. Yeah. So this is our API server, and I'm going through, something that you may be interested is it's still very small. The runtime itself, the Watson Edge runtime, it will take 10 or 20 megabytes because you have to handle the the dependencies and lots of things. But the Watson application is pretty small, just as I mentioned before. And you can run this software stack on a very small device, such as the Raspberry Pi 4, or if you have a small NVIDIA Jackson device, you can still deploy it on it. So it's pretty cheap. You don't need to have the super expensive NVIDIA H100 cluster. No. You don't need that. You just need a very cheap devices to run all of the stacks. And also, we are not only support the GPU, we are also using the TPU on some hardware devices. For example, we are now integrate the Qualcomm SDK to leverage the Qualcomm ML library to do the acceleration. So that's what we care about. But the developer don't worry about that. It just install and run. Yeah. And the second one is that we already simplify the installation. So most of the case, you don't need to install the software stack using the root mode. You can use the unprivileged mode to install it. And also, even I just show the Llama 3 model, actually you can try the mixed trail MOE model, or you can try lots of different model, which is already supported by our software stack. But the model is huge, and this computer has a small device, small desk specs, so I cannot download all of the model and show you. So you can use your own computer to do that. And now we already integrated some hardware framework, such as the CUDA, and we are working on the Tensor runtime. And also, if you are using the Apple Silicon, then we are using the Metal framework, but we will have the MLX support soon. So after that, I believe you can run not only the basic LLM, you can also run the Stable Diffusion and other different AI model then. And we actually customize the hardware optimization on different CPU. If you will have the server-side CPU, we will try to enable the AVX 512 to accelerate the matrix speed, computation speed. And after the hardware part, then we want to, in our API server, we already have some formatted response, so you can do the function calling, just like you interact with the OpenAI server. And also, we have the IIG demonstration, and this is our next demo. So I will show the demo then. Then the idea is that we want to create a portable application, which is you only write your logic once using Rust or Kotlin or other language, and then compile it into WebAssembly. And just like you have lots of the APK files on Android, and you distribute those applications to your user, then your user can just run it with no other issue, and they don't need to worry about the hardware part or any details. Yeah. So the second one is that we don't have the Python dependence, so you don't need to worry about that. You have to install Python first. Python maybe take 40 or 50 megabytes, and you concern your disk specs. So let's see the RH application. We have an integration here. Is we integrate with the GaiaNet. It's a super easy command line to manage the whole, for example, the models, the configurations, and all of those things. So you can see here we have the config.json, and you can very easy to change your chat model and change your prompt template. And also, if you want, you can. We have the embedded model. You can also change the embedded model, and you can change the snapshot. In this demo, I already use the. I already passed some, the Paris data as an embedded snapshot. So when I ask anything related to Paris, it will just look up the embedded database, not using the model itself. So let's see this demo. And because I already set up it, and due to the network environment, it's not possible to do the initialization work here because it will download all of the model. So if you're interested, you can, just run this init by yourself, and it will take time. Okay, so let's do the start with the local only, and you will create the QCron database, and then you will load our snapshot into the database. Then you will check the output from the previous snapshot. So let's, when you execute the GaiaNet, and you will, you will see this dashboard. You just check the chat with this node, and you can say where is Paris. Before we are doing this, we need to check the log here. Here is that we just, initialize the GaiaNet, and we are waiting for the input from the website. So I'm talking about where is the Paris, and then it's doing, and then it shows some information from the database. How can I prove that it's showing on the database, not JavaScript behind, and say, hey, if I ask this question, just return this, okay? So here is the thing that when user query where is the Paris, you will try to embed your query into the request JSON format here. So you will try to ask the embedded model and with this input, and the embedding will be specified into the chunks, and these chunks will be look up from the database. So you can see there's lots of log, and we are doing the computation, and then we find we compute the output from the embeddings, and we retrieve the context. For example, we have the 0.1, 0.2, and you have different scores. You have lots of different souls. So combine all of them, then you will have the output and send to user. So in this demonstration, actually, you can just modify the snapshot. For example, you can do the Amsterdam embedding snapshot, and then you can ask the related question. You will just look up from this embedded database. Yep. So that's the demonstration of the IIG application, and I believe it's a little bit small, but the basic idea here is that when the node is on, then you will have the URL, so everyone can link to this URL and interact with your node. And then most of the idea is that the high level is the API server, just a customized API server for this IIG example. And you can interact just like you interact with the OpenAI server. And all of thing is that we also embedded the knowledge embedding in the vector database. So you can also install more different knowledge embedding here. And when the front-end side receive any request, you will just check the vector database here. And then at the bottom is our Watson Edge runtime. You will try to leverage all of your hardware resource, for example, the CPU, GPU, or TPU. Yeah, so this is the software stack, and that's how we, the first demo is that we only use the bottom part, and the second demo we are using the up part, and then the IIG demo we are using all of the parts. So that's why I split it into 3 different demos to show the idea of the Llama Edge. So if all of things is done, what is the special things that we can do is that we are introducing the lightweight LLM containers. You can just run the same things inside the Docker or inside the Podman. Yep. So because the setup takes some configuration, so you have to check this document for the details. But the idea is that there are several different ways to integrate Docker or container with the LLM runtime. The first thing is very naive. You just create a normal Linux container, and you install the Llama Edge, you install all of the things, and you are just running a Linux container. So it will take lots of disk space. It will take, you need to install the NVIDIA Docker Machine. You need to install the correct CUDA driver. You need to care all about this. So this is the naive way, but this not we really want. We really want is that we hope the Docker or container or Kubernetes, it can only register the container device interface. For example, you just need to tell your container management, hey, I have a GPU, which is maybe the NVIDIA GPU or something like that. And we don't need to specify the environment. We only need to do is that when the Docker plus the CDI with our Watson runtime, you can only ship your applications with a very simple layer, which only contain the WebAssembly itself. You don't need to package the Linux container. You don't need to package the CUDA runtime. You don't need to package all of this, because this is offload to the CDI and the Watson runtime itself. All you need to do is to install the normal Docker desktop and just, the plug-in system. You just put Watson Edge with the Docker, you just put CDI with Docker, then okay, then it's gone. Yep. So that's all I have. I forget to show the most important demo. This is the Docker run, right? I just run the Llama 2, and the network is gone. No, the network is gone. Anyway, you just imagine that if this command is pushed, and it will do the inference and tell you that, my question is, what's the capital of Japan? And the answer is Tokyo. Yep. So I already run out of time, but you can try our demonstration by yourself. And yep, that's all. Thank you. If you have any questions.